Hey everyone, and welcome. Today, we're going to pull back the curtain on the simple, elegant principles that power, well, almost everything. From ancient wonders to the coolest modern marvels, we're talking about simple machines. Think of them as the hidden toolkit, the secret code behind pretty much all of mechanical engineering. All right, let's jump right in. So it kind of sounds like a riddle, doesn't it? I mean, what on earth could a giant stone pyramid possibly have in common with a sleek, high-speed competition robot? Well, the answer is this secret set of 6 fundamental tools that really haven't changed in thousands of years. And trust me, by the time we're done here, you'll see the exact same physics playing out in both.
Okay, but before we can even crack open that toolkit, there's something we've got to get straight. There is one single, unbreakable rule that governs every machine, whether it's simple or super complex. You could call it the golden rule, the absolute law of the land for any engineer.
And to get a handle on these machines, we have to talk about the word work. Now, in physics, work has nothing to do with how tired you feel after a long day. Nope, it's way simpler. It's just a force applied over a certain distance. That's it. This one little formula, work equals force times distance, is honestly the key to unlocking everything else.
And that formula leads us straight to that golden rule I mentioned, what physicists call the no free lunch principle. It's pretty simple, really. A machine can't just create energy out of thin air. It can't give you something for nothing. Because energy is always conserved, the amount of work you put into an ideal machine is exactly what you get out of it. Which brings up a pretty big question, right? If machines don't actually reduce the work, then what's the point of it?
Well, this is the secret sauce. This is the clever little loophole that every single simple machine is designed to exploit. See, they can't change the amount of work, but they can absolutely change how you do that work. It's all about a trade-off. You can trade force for distance. So you can use a small, easy-to-manage force over a long distance to get the exact same result as using a massive, back-breaking force over a short distance. That is the whole game.
All right, so now that we've got that golden rule locked in, it's time. Let's finally open up that toolkit and meet the 6 classical simple machines. I'm telling you, these are the fundamental building blocks that engineers, from the folks building pyramids thousands of years ago to the roboticists of today, have used to literally build our world. First up on our tour, let's check out 2 machines that are all about rotation. We're talking about the lever and its very famous cousin, the wheel and axle. The lever is probably the one you remember from science class, right? It's the classic. Just picture a seesaw, or maybe using a crowbar to pry up a huge rock. All it is a stiff bar and a pivot point, which we call the fulcrum. And by pushing down on the long end, you get this huge lifting force on the short end. That's our force for distance trade-off in its purest form. And believe me, this tool is timeless. I mean, think about it. Back in the 13th century, you had engineers building these enormous cranes, all based on levers, to hoist 3-ton stones way up high to build cathedrals. And now, today, a competition robot uses the exact same principle in its lifting arm to move stuff around with incredible precision. It's amazing. So what happens if you take that lever idea and just let it spin all the way around its pivot point? Well, you get a wheel and axle. It's that simple. The center axle is the fulcrum, and when you apply a little bit of force to the big outer wheel, you create a much stronger force at the axle. It's basically a lever that just keeps on going, one that never runs out of room. And you use this thing all day long without even realizing it. A doorknob. That's a perfect example. The knob you turn is the wheel, and the little shaft inside is the axle. But that same simple idea can be scaled up to do some pretty incredible things. You look at modern robotics teams, and they're building these insane high-speed ball shooters, where a motor spins an axle to get a wheel moving so fast it can launch a ball with a ton of energy. All right, let's dig back into the toolkit for our next set of tools. And what's cool about these next 3 is that they're all basically part of the same family. They all come from one super simple idea, the ramp. So first up, you've got the inclined plane itself. Yep, just a ramp. It lets you push something heavy up to a new height with way less effort. Okay, simple enough. Now, what if you stick 2 of those ramps back to back? Boom, you've got a wedge, perfect for splitting things apart. And then, for the coolest trick, take that flat ramp and wrap it around a cylinder, and you get a screw, which is amazing at turning a twisting motion into a powerful straight-line force. You can see how they all share the same DNA, right? You know, the most famous use of the inclined plane in history has to be the ancient Egyptians, right? Building these absolutely massive ramps to haul giant stone blocks up the pyramids. An incredible feat of engineering. So now, you fast forward thousands of years to today, and what does a high-tech robotics team build? You guessed it, a ramp. It's an intake for their robot, using the exact same physics to guide balls up into the machine with as little force as possible. Some ideas are just timeless.
Okay, so we've met the individual tools, the players on the field, but the real magic, the real genius, happens when you start putting them together on the same team. See, most of the powerful and useful things we invent aren't just one simple machine. They're combinations of them. We call them compound machines.
I mean, just take a look at something as ordinary as a pair of nail clippers. You probably never think about it, but this little thing is a brilliant piece of engineering. You've got the first lever that you push down on. That lever then pushes on a second, much more powerful lever. And the actual cutting edges, those are just two tiny wedges. That's three simple machines all working together perfectly to turn your weak finger press into a super strong cutting force. Or think about a bicycle. It's this beautiful symphony of simple machines. You've got wheels and axles, obviously, for rolling around. You've got levers in the handlebars and the brake handles. The chain and gears, that's just a fancy pulley system, which itself is really just a modified wheel and axle. And of course, you've got screws everywhere holding the whole thing together. It looks complex, but it's all built from these simple, elegant parts. Now, up until this point, we've kind of been living in a perfect little physics fantasy land, right? Where all the work you put in magically comes out the other side. But, as any engineer will tell you, the real world is a lot messier than that. And the main reason for that messiness, the big villain of our story, is a force we absolutely cannot ignore: friction. And I want you to look at this number. This isn't just something from a textbook. This is a real-world measurement from a lab. Scientists were testing a specific machine called a differential wheel and axle. It's a clever setup that gives you a massive mechanical advantage. But when they measured it, they found its real-world efficiency was only 62.53%. Just think about that. That means more than a third of all the energy they put into the machine just vanished. It was lost to heat because of friction.
And here's a look at the actual rig from that experiment. This isn't some clean computer drawing, it's the real deal. And you can just imagine every single point where these parts rub and turn and touch, friction is there, just stealing a little bit of energy. And that right there is the constant battle for every single engineer, trying to bridge that gap between the perfect, clean world of the formulas and the messy physical reality where the work you put in always has to be more than the work you get out.
You know, the ancient Greek genius Archimedes captured this perfect, theoretical power of simple machines with this famous quote. He said, "Give me a place to stand and I shall move the earth with a lever." And you know what? In a perfect, frictionless universe, he was absolutely right. A long enough lever could do.
But that brings us right back down to earth, doesn't it? Archimedes' idea is beautiful, and it's true, in that perfect world. But here, in our world with all its friction, that no free lunch rule always gets the last laugh. And so the real question, the one every engineer faces every single day, isn't just if you can move the world. It's how much extra work are you actually willing to do to fight back against all that friction that is always there pushing against you.